you will have a problem like this. I want you to give it a try first, then I'll solve it. Okay, so I'm helping you out too. And actually, this is a WebAssign problem. You have a WebAssign problem like this. And you have a lot of WebAssign. I pushed out the WebAssign. Don't wait till the last minute, but I pushed out a lot of the WebAssign to August 14th. Okay, so but make sure you get it, make sure you get that done. All right, so try to solve this problem here, and then I'll solve it. But I want to give you a chance to try to do it first. What's with the attendance? Okay, so everybody should be working the problem that I have here. And don't forget, when you divide this through, you divide this by x, right? And so, but x is a singular point, but it's a regular singular point, so I can use the method of Fabenius. For people that just came on, we're trying to solve this differential equation, and then I'm going to solve it. And the roots turn out to be 0 and 4/3. And you will get a problem like this on the next exam. So I want to make sure everybody gets it right. So we're going to finish up power series today. These problems do take a while. I'm going to give you at least 15 minutes to try to do it. And only do the first 3 terms, okay? On the exam too, I just want you to do the first 3 terms. So right now, you're also working the WebAssign problem. The thing is, though, instead of having a 3 here, you could have a 2. And you could have a 2 here. So the numbers are going to be different, but this is a WebAssign problem.
Professor, can I have permission to record, please?
Who just spoke?
Connor?
Okay. All right. It says that you have permission to record.
Okay, thank you.
Right, I think a couple of people just got on. So what we're doing, we're trying to solve this. You're trying to solve this differential equation, okay, using the method of Fabinus, and then I'm going to solve it. But I want you to give the, you will have a problem like this on the next exam. So you need to make sure you know how to solve this. Has anybody got R1 and R2? Well, take some time to get there. We're normally getting R1 and R2 is not that hard. It doesn't take that long. Has anybody got R1 and R2 as being 0 and 4/3? Nobody? Oh boy. Chat. I'm gonna give you another 2 minutes. Hope you're making progress on this. Even if you get it's always good to give it a try. And then, and then like learn from your mistakes, what you did wrong. So we're going to finish up with power series today. And if you could do this problem here, once again, you'll be in good shape for the exam. At least for this, for the power series part of the exam.
So I have a quick question.
Sure.
We're taking the third exam today, right?
No, we'll take the third exam on Tuesday. I don't want to give a differential equations exam. I don't want to give I don't want to give an exam that's just power series. I want to do a little bit of Laplace transform.
Oh, okay.
Because if I do that, if you end up getting a problem wrong, then you could really get a really low grade.
Okay. Thank you.
Yeah, so the next exam will also be on Tuesday. Okay, so all right, let me go ahead and solve this differential equation. But first, I just want you to realize that, if we rewrite this like this, I'll keep the 3 here. No, that would be let me rewrite it like this. You'll get it in the form where this is y prime now divided by 3x, and then I got plus y divided by x equals to 0. Okay. Now x here is a singular point, right? But it's a regular singular point because remember now the rule is that if I have if I multiply this by x, if I'm expanding about 0 and this is about x squared, then this is a singular point, but it's a regular singular point. Okay. So for this differential equation, right, I can assume a solution that I can assume a form of y is equal to the summation m is equal to 0 to infinity of right. I can assume a solution of that form, right? So then y prime. Now, when we do the method of Frobenius, we have to continue. We have to be at 0, right? With the other method, I could start at 1 because I'm bringing down and n, right? And when n is equal to 0, but when I have this r here, I still have to start from 0. So this is going to be, let's see, this will be c to the n plus r, right? And then this is going to be x to the n plus r minus 1, right? And then y double prime would be c to the n plus r, right? N plus r minus 1, and then this is x to the n plus r minus 2, right? When I take the derivative. Okay, so now I'm going to take y double prime, y prime, and y, and substitute it into my differential equation. All right, so let's see. So so first, when I have a 3x here, right? I have a 3x here. So I'm going to write this as a summation. N is equal to 0 to infinity, and I'm going to bring in the 3, and then I'm going to write this as Cn n plus r, right? N plus r minus 1, and I'm going to write this as x to the n plus r minus 1, right? Here I got a minus 2, right? But here I got an x. So when I bring the x in here, right? When I bring the x in here, that's going to make this a minus 1. Okay, and then I have a minus summation, n goes from 0 to infinity. And let's see. So this is going to be c to the n plus r, x to the n plus r minus 1. And now I have plus summation, n goes from 0 to infinity. And now my y is going to be 3, right? I have to put this, I'm going to put this 3 here, and then it's c to the n, and then x to the n plus r, and that's all equal to 0. Okay, let's see, I got everything right, I copied everything right. Okay, good. All right, now, I need to get the powers of x the same, right? I need to get the powers of x the same, right? That's the next thing. We need to get the powers of x the same. I'm going to leave this alone. Okay. Notice lots of questions. Why do you leave this alone? We leave this alone because it's n plus r. I want everything to be n plus r. All right. So the way I like to do it, I'm going to make a change of variables. Right. Let's see. I'm going to say that. Let's see. I'm going to say that the k is equal to n minus 1. So therefore, k plus 1 is equal to n, and when let's see, when n is equal to 0, right? When n is equal to 0, k is equal to minus 1, and I'm going to do the same thing for this one too, right? N minus 1, and then this is going to be k plus 1 is equal to n, and when n is equal to 0, k is equal to minus 1. This I'm going to leave alone. I'm just going to say n is equal to k. Right? All right, so now what do I got? Okay, so now I'm going to get summation, right? This is going to be k is equal to minus 1. Right, k is equal to minus 1. That looks like a plus sign. K is equal to minus 1 to infinity. Now this is 3. Now this is going to be c to the k plus 1, right? Because when, okay, and then I'm going to get I'm going to get k plus 1 here plus r, and then this one here, right? When I'm going to put right in the place of n, I'm putting the k plus 1, right? And here I got an n, so this is going to be let's see, this is k plus 1, and here I got the 1, so this is just going to be k plus r, right? This is just going to be k plus r, and then x to the then I got x. Now remember now, K plus R, right? That's what I did. I want to make this K plus R. Okay, so now here now I get summation. Once again, K is going to go from -1 to infinity. And then this is going to be C to the K plus 1. And then this is, let's see, so this is going to be K plus 1 plus R, right? And now here, finally, I'll move it back over, but here now, this is going to be plus 3 summation. Now it's K is going to start from 0. I'm just making K is equal to, I'll make it N is equal to K. So it's going to be 3, and then this is K, and then this is X to the K plus R. And this is equal to 0. Okay. All right, let me, so far so good. Okay. All right, so now what's the next step? So now we got the, right, I got this X plus R here. I left out an X plus R here. I left out the X. This is going to be K plus 1 plus R. And then I got the X to the K plus R. Okay, so now I got my powers of X the same, right? So the next thing we need to do is that, and this is going to give us the values of R, all right? This starts from -1, this starts from -1, and this starts from 0, right? So I want everything to start from 0, and then I can combine everything all with one summation sign to get my recursion relationship, okay? So once again, when you do about an ordinary points, you do the same thing. So let's see. So the next thing I'm going to do, let me do this. I'm going to write out the first term here, right? So let me write out the first term here. So when I write out the first term here, I get 3, and then this is going to be 0, right? Because I'm putting a -1 in here. Now this is 0, right? This is 0. No, let's see. I'm putting a -1 in here. So this is just going to be R, right? This is just going to be R here, right? When I put a -1 here, this is R. And then this is going to be -1 plus R, right? And then this is X to the K plus R, right? So I just expanded out the first term. Here too, I got to expand out the first term. So now I'm going to get a minus, let's see, minus, and this is going to be a C0. Now when I put a -1 in here, so this is just going to be R, right? This is just going to be R. And this whole thing is times X to the -1 plus R, right? Because K is -1, right? And then I have, now everything is starting from, I'm not going to copy it all, but everything now, there'd be a plus sign here. But everything now here will be under a common summation sign, starting with K equals 0, all right? So let me work on this, okay? This here now is going to give me my values of R, right? So let's see. So let me do this. Let's see. So I guess first, let me factor out a C0. I can factor out a C0. And I get 3R, right? Factoring out the 3, -1 plus R. This is also, well, let me do this. I put it out here. I don't need it here. I don't need it here. I have it out here. And so as all I'm doing here is factoring out a C to the 0. So factor out C to the 0. And then this is times this. And this whole thing has to equal 0, right? Term by term, this whole equation equals 0. So term by term, you have to equal 0. Now we know that C0 is going to be an arbitrary constant. That's not equal to 0. And this is not equal to 0. Right? So therefore, what I have in the parentheses has to be equal to 0, right? So let's see. So what does this become? Let's see. So this, what I have in the parentheses, this is going to be 3r minus 3r plus 3r squared minus r is equal to 0, right? So I can write this as 3r squared minus 4r is equal to 0, right? Okay, I can factor out an r, and I get 3r minus 4 is equal to 0. So this is telling me that r is equal to 0, and 3r minus 4 is equal to 0. So just tell me that r is equal to 4 over 3. All right, so that's it. Those are my, so I got r is equal to, r2 is equal to 0, and r3 and r1 is equal to 4 over 3. Remember, we take the larger value, and you'll see why. You don't have to do this, but it explains something else that I'm going to talk about. But I'm not going to ask you about it on a test. Okay. So any questions? So now I got you know, I'm going to break up the points in terms of if you get R1 and R2, that'll be 1/3 of the credit. If you get the recursion relationship, that'll be another third of the credit. And then when you get the assemble it and get the right coefficients, that'll be 1/3 of the credit. Okay, so like problem like this could be 15 points. It'll be 5 points, 5 points, and 5 points. That's what I've done in the past. Okay, so now I got R1 and R2. I got my R values. Okay, so let's see. So now I want to get my recursion relationship. So so let me do this. I got everything starts from 0 now. So I can write this like this. I can write this summation. K goes from 0 to infinity of 3. I'm just copying this down here. I'm copying down what I have here, but starting now with K is equal to 0 because I expanded out the -1. So let's see. So okay. All right. So so this is what I have now. Let's see. Looks good. Make sure I didn't make a mistake. This stuff isn't hard. All right. So what do I want to do now, right? I want to get a recursion relation. So I want to solve for C subscript K plus 1, right? I want to solve for subscript K plus 1. Let's see. So what's the easiest way to do this? Okay. I'll factor out the CK plus 1, right? So this is going to give me a 3. This is the easiest way to do 3. Then I'm going to K. All right, just factoring that out. And I'll bring this over to this side here. Right? So I brought this over to this side, right? So what I'm doing is this can't be 0, so I'm setting this equal to 0, right? Setting what I have into the brackets here, I'm setting that equal to 0. So then I'm bringing this over to this side of the equation. All right, so now, okay, so now I got my recursion relationship. Okay. So let's see. So my recursion relationship, we do it like this. My recursion relationship is that I'm going to get it's equal to -3, right? And then down here, I get 3 k plus 1 plus r, k plus r, minus k plus 1 plus r. Okay, let me see if that's all right. Okay, it's good. I really don't need these brackets, but that's okay. All right, so now I'm going to do, so this is recursion relationship, but I'm going to get two recursion relationships. It turns out that, I'm going to get two linear independent solutions. One for r is equal to 0, and the other is for r is equal to, what was it, 4/3? Yeah, 4/3. So I'm going to put r is equal to 0 in here. So for r is equal to 0, let's see. I get rid of this here. So for r is equal to 0, I'm going to get and this is going to be 3 and 3k. I guess this will be 3k plus 1, right? K plus 1, r is 0 times k, and then minus k plus 1, right? So that's for r is equal to 0. Okay. Now what about r is equal to 4/3? Okay, this is a little bit messier. So now I'm just going to plug in place of r, I'm going to put in the 4/3, right? So it's going to be minus. Now I'm going to have a 3. I'm going to write this as k plus 1 plus 4/3. Should have left myself more room. This is k plus 4/3. And then this is minus k plus 1 plus 4/3. Okay. Should have left myself some more room. All right. So now I could continue. I could work with this, right? I don't want to deal with fractions. In other words, now I could just start finding what for this one here. I could put in what 0 is and get what k1 is, and so on. Put in what k1 is and get k2. Put in k3 and get k4. All right. I want to simplify this because I don't want to deal with the fractions. All right. So what I'm going to do is I'm going to factor a 3 out of here. Right. So this is going to become, and then this is going to become 3k. Now this is going to become plus 7, right? Because when I factor a 3 out of here, this becomes 3, right? And then I have the 4, so this is going to become plus 7, right? Then I'm going to do the same thing here. I'm going to factor out a 3 because I don't want to have to deal with the fractions. Factor out a 3. And when I factor out a 3 here, this will become plus 4, right? And then here too, I'm going to factor out a 3. And this is going to become, well, this 2, there's a 4 here. This is a 4, right? Yeah, this is a 4. So this 2 here, this is going to become 3k plus 7, right? When I put the 3 back in here, right, this is going to become a 3, right? Hope everybody sees that. Okay, so so this 3, right, this 3, I can cancel with this 3, all right? Now, here I got a 1/3 and here I got a 1/3. So I'm going to write this, and you don't have to do it this way. You can just continue in dealing with the fractions, but you write this like this. Oh, this is gonna be 9 now. Right, why is this 9? This is 9. See, here I got a 1/3 at the bottom, here I got a 1/3 at the bottom. So I multiply both up and down by 3, right? So this will become 9. See, now I got rid of my fractions. Like I said, you don't have to do it this way. Okay, so that's my recursion relationship. Make sure it looks good. Okay. All right. So you could just deal with this if you want to keep dealing with the fractions, but it's going to be a lot easier to deal with this. Okay. Now, I just want to do the first 3 terms, okay, for each one of these. So let's see now. So we start out with C0, right? We start out with C0. C0 is not equal to 0. C0 is going to be our arbitrary constant, okay? Now here we're going to have C0 too. So it's one of them we're going to have to change. You'll see what I mean in a minute, okay? So we start out here with C0, all right? So let's see. So that means that C1 is going to be equal to -3 C0. Well, let's see, when I put, what am I going to get here? When this is 0, this is going to be 0, right? And this is going to be, yeah, this is 0. Hold on a second. Okay, and so this is going to be 0, and then this is going to be when I put 0 in here, so this is going to be -1, right? This is 0, right? And this is -1. So this is telling me that C1 is just going to be equal to 3 times C0, right? That's what C1 is, okay? And let's just do C2. C2, remember now, C2 is going to be equal to -3 times C1, right? And now I have to put 1 in here. So there's going to be 3 times 2, right? Times 1, right? I'm putting 1 in here, -2. -2.
Excuse me, Professor.
Yes.
For C1, if you plug in k is equal to 0 for the initial value, wouldn't that instead be 3C0 over 0? That
No.
undefined?
No, I have the 1 here. This is 0. You're right. This is 0. But this, when I put 0 in here, this is -1. Right? There's a minus sign here.
Oh, yeah, you're right. You're right. Yeah, okay. Sorry.
No problem. Okay, it's easy to make a mistake. Like I said, they're not hard. I tell you, there was one time I was solving. It was actually it was a partial differential equation where you had to break it down. It was actually coming up with the orbitals for doing the shapes of the orbitals that you're learning in chemistry. You know, in chemistry, you learn about the different shapes of the orbitals. Turns out that comes from a partial differential equation that you break down into ordinary differential equations, and then you solve them using power series. Okay, and anyway, it turns out that when you do that, you end up getting truncated polynomials. But I was having a problem where I knew what the answer had to be, and I wasn't getting it right. And I kept on making a mistake that I kept on saying that 3 times 2 was 5 instead of 6. Drove me crazy. So anyway, all right. So let's see. So back to here. All right. So now let's see. So this is, I got -3C1. So this is going to be 6. 6 minus 2. So that's going to be 4. Right? 6 minus 2 is 4. And then C2 then, in terms of C0, is going to be minus, right? It's going to be -9/4 times C0. Okay. So let's see. So this is what I got. Let me we need to assemble the final answer. So let's see. So here I got, C0 is our arbitrary constant, and this is C1, and then this is C2. All right, I'm not going to do it. We'll just do 3 terms. That's the first 3 terms. Okay. All right. Let me. So in other words, one solution is actually going to be like this. One solution, I'll call it white. One solution is going to be. Let's see. Well, let me put in the C0. So it's going to be C0, and then it's going to be plus. It's going to be C0. Well, let me do. I'll do it the long way. And then it's going to be 3 C0 times X. Right. This is X. Right. So in other words, the C1 is going to go with X. Right. And then there's going to be minus 9/4 C0 X squared, and then higher order terms. But that's good enough. Right. We'll just do the first 3 terms. The same thing on the exam. Just do the first 3 terms. Okay. So I'm getting now that my Y1, one of my solutions, I can write a C0, 1 plus 3x. I'm just factoring out the 30 minus 9/4 x squared plus dot, and then there's higher order terms. So that's one solution to the differential equation. Now with the other R value, we'll get the other solution. All right, so this is one solution. So let's get the other solution. And once again, I need another paper. Okay, so now we're getting the other solution. Okay. All right, so now I'm working with this one. So let's see. So let's see how this is going to work out. Let's see here. Okay. Let's see. So I'm going to get C1 is equal to minus 9 C0. Now I'm going to put 1 in here. So when I put 1 in here, this is going to give me 10. Right? When I put 1 in, well, first I want to put 0 in here. Right? First I'm putting 0 in here. So this is going to give me 7 times, this is 0 times 4 minus 7. Okay. So let's see. So this is going to become, let me simplify this. This becomes 28, right? This becomes 20, this becomes 21, right? 21 over 9 C0. So C1, I want to get the answer that's in the Weber sign. That's why I'm simplifying it. This is minus 3 over 7. Yeah. C0. Okay, so that's what C1 is. C1 is minus 3 over 7 times C0. And let's just do one more. C2 is going to be minus 9 C1. Now I'm putting in, I have to put in a 1 for this, right? So now I'm putting K is equal to 1. So this is going to be 10, right? 3 plus 7 is 10. And then this is going to be 7, right? Minus, and then this is going to be 10. And so what do we get here? So now I'm getting C2 is equal to minus, now let's see, this is 70 minus 10, so this is 60. This is 60. But I want to get this in terms of C0. All right, so this is going to be, let's see, it's going to be minus 9, then it's going to be minus 3, 60 times 7, right? C0, right? This is, right, in place of C1, I put in this here, right? So let's see. So, see, the 3 goes into 60 20 times, right? This becomes a plus. So I'm getting that C2 is equal to, C2 is equal to 9 over 140, right? 20 times 7 is 140, right? This is 1, and that's, right? The 3 goes into the 60 20 times, C0, and it's plus. Okay, so that's what X2 is. So my other solution would be 1. Well, let's see, I got to be careful now. My other solution now, well, maybe I should do it. Let's see. Let me do it like this. My other solution is going to be X. Now it's going to be to the, well, what was it, 4/3? It was 4/3, right? Remember, R is to the 4/3 now for this one. So it's 4/3 plus 0, right? And okay, so that's my first term. My second term is going to be minus. My second term is going to be minus 9 over 21, C0, and then it's going to be X to the 4/3 plus 1, right? Plus 1. And then the next term, right? The next term is going to be, this is minus b plus 9 over 140, C0, X to the 4/3 plus 2, right? Plus higher order terms, 4/3. Now, you see, I can write this, I can factor out the C0 now. I can write it like this. It's higher order terms. Okay. All right. So so this is Y2, right? That's Y2. In terms of the constant C0, right? That's Y2. Now let's let me write the whole thing out. Let's see, what did I guess I need another sheet of paper. Okay, so this is what we got. Okay, now we need to, so this is our Y2. Remember, we had the Y1. Let me write the Y1 again. Where is the Y1? Okay, here we go. Let me do it this way. Okay. So here's our answer. This is Y1 and this is Y2. Now, in some of the WebAssigns, they actually don't even have any constant. I think with the, they just want to know what's called a fundamental function, right? So you wouldn't have any. So, but if I wanted to write this as a final solution, you know, I should probably call this 1 and this 2. You know, I shouldn't call this C1 and this C2. You know, these are initial conditions that have to do with, I mean, these will be determined by, you know, if we have initial conditions. So these two constants are not the same, all right? So you have to keep that in mind that, you know, I can call this C1 and I should call this C2, okay? So that's my total answer. So that's the answer. This would be C1 and this would be C2. Now your WebAssign made it a little bit easier. Like I said, this is what we just did is a WebAssign problem. And to get the answer in the WebAssign problem, you just need to do, but let me do something here. Hopefully I got it right.
Excuse me, Professor.
Yeah.
So how will we enter in into WebAssign the ... to to say like, oh, there's more following terms.
Well, I'm gonna show you now. You don't have to do it actually,
Oh, okay.
okay? The WebAssign problems look like this. I'm getting to it now. I guess maybe that's why I never realized. That's probably why they did it. Okay. Okay, do you see my screen?
Yeah.
Okay, so here's the problem we
Yeah.
just did, right? So here's the problem we just did. This is the differential equation, right? Here's the R values. And you see with the WebAssign, you just have to pick the right solution. Okay, so okay, so this is right. So this would be the right answer. Now I have this as 9/21. If you take a look at what I wrote down, so this is 3/7 is the same as 9/21, right? And we only did the first three terms. So on the exam, just do the first three terms. You don't need to do four terms. Okay, so so we got the right answer. Okay, any questions?
Uh,
So these are, yeah, go ahead. Go ahead.
Can you go back to the paper you were working on? Can you repeat again how you got the R values?
Sure. See, let me find that sheet of paper. There's actually another way of getting the R value, which I was going to show you, but you're not responsible for. Where is it? Let's see. Let me find it. I should have. Okay, here. Okay. The way we got the R values is right. We expanded this out, right? In other words, this starts from k equals 0. This starts from k equals -1, and this starts from k equals -1, right? So I wrote out the first term. I wrote out, so this is the first term, right? When I put -1 in here, right? I put a -1 in here, then that's just going to give me R, because -1 + 1 is 0, so that gives me R. And I put the -1 in here, so that gives me the -1 + R, right? And then here, I'm putting in a -1, so that's just giving me R, right?
Right.
That, okay. So then what we do, where's the next page? This is the next page. So then what we do is I factored out this is not equal to 0, and this is not equal to 0. So then we're setting this equal to 0, and we're solving for R, right? We're solving this for R, right?
Oh, okay.
Set this, okay. So see, I get this now. I get this -3R + 3R squared minus R, right? When I bring this through here, this times this is giving me the -3R, and then this is 3R squared minus R, right?
Yeah.
And then this times this gives me a -4R. I factor out the R, and that's how I get the R is equal to 0 and R is equal to 4/3. Okay.
Okay.
Not hard. They're just they're long. Am I right?
Yeah. Professor.
Yes.
So I understand that you're trying to get the R values alone so you can get to this step, but does the K value have to be the number that it's starting from to?
Yes.
Yes. So it can't just be any number. It has to be the starting value to get just R.
Well, once I get, let's see, when I get the recursion relationship, right? When I get the recursion relationship, well, state your question again. Maybe I don't understand you.
Sorry. Can you go back to the previous page when you were plugging in K -1?
Yes. Yeah.
So yeah. So does K always have to be -1 in this case because it starts at K -1 to get it to R alone? Or is it just conveniently that K just -1 and it just can't?
No, in this case, it may turn out that, it could turn out that you get K -2 or something,
Right.
in which case you would have to send out 2. It depends upon, the powers that you have here. It's going to depend upon this. This may not always be, although I think on the one I gave you, problem I gave you is very similar to this. Okay. But anyway, this may not, for example, if we didn't have the X here, then this would start from 0.
Oh, sorry. Let me rephrase my question. All we have to do is just plug in the K value into that, and then we can just solve for R, right?
Correct.
Okay. So no other values would work.
Right.
It would only
No,
be K.
well, the reason why I'm putting K equals K is equal to -1 here is because I want to start all my summations at K is equal to 0.
Oh, okay. So
Right?
there's two reasons that's why you do. Okay, I see.
Right. In all of these problems, the 2 important things is getting the exponent the same, right? You want to get the exponents all the same. And that's what we do this trick here where we change, these are called dummy variables. We can change the dummy variables. And then we want to get the summations the same. And those are the 2 things, both in this type of problem and the other type of problem. We want to get the summations the same, and we want to get the powers of the exponent in X the same. Okay. Did I answer your question?
Yes, thank you, Professor.
Okay. All right.
Professor, I
Yes.
have one question. In the first page, can you please go over how you find your the function that start with C0, with C0?
First page. You
Yeah,
mean this page
When we
here?
just started- Yes, when we just started the problem. If you go down,
Yeah, I think that, hold on a second. I don't know. You mean here, this is the first page.
yes, if you scoot your paper a little bit down so I can see. So like here, to your last equation,
Right,
we just plugged in K is equal to -1 to find
Right.
the 3C0.
correct.
All right,
I have everything here now starting from 0. And so all I'm doing is I'm putting K is -1 here, right? My summation starts at K is equal to -1. I want to start at 0. All right, so I'm taking out, I'm putting in K is equal to -1, and then I can start everything from 0,
oh, okay.
right? Right, this starts at -1, and this starts at -1, right? So now I get this, and this is actually going to give me what my values of R is going to be, and then now everything's starting from 0. So now I have all my exponents the same, and the summation starting from 0, and then I can get the recursion relationship. Okay.
All right, thank you. And then for the summation in the equation up, is it from infinity to n is equal to 1 or n is equal to 0?
No, here this is K goes from, yeah, you could say N, but yeah,
No,
this
not
goes from
here.
0 to infinity.
Above, not here. In the second equation, above where you wrote K is equal to n-1, above it. So when you started writing with the summation, no,
Right
not
here?
No, up,
Yeah,
still up. Here at the beginning.
right. Yeah,
No, down. If you go down all the way to the left,
yeah.
all the way to the left of the page.
Oh, left. Okay.
Yeah. Yeah, the beginning is summation from infinity to n is equal to 1 or n is equal to 0.
Right. This is from 0 to infinity,
Oh, okay.
right? And
Yes.
this is from 0 to infinity. This is from 0 to infinity. But what happened was is when I made this transformation, right? This started now with -1, right? And when I made this transformation, it started at -1. So in other words, when I made this, right, I caused this now to start at -1, and I caused this to start at -1, right? This stayed the same. So now this is starting at -1, this is starting at -1, this is 0. I want them all to start at -1, so I write out the first term with -1. Write out the first term with -1, and it gives me this.
All right, thank you, gotcha.
Okay. Let me I have a let me just go to my notes here. Let's see. Come on. Oh, wait a second. It's not. That's what I want here. Okay. Let me make sure that. Okay. 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 So this is the problem we did yesterday. So, you can go over. I use I use something called MathType to make it all look really nice and neat. Takes me a long time. Took me a long time to do these. Okay, but I just want to show you a couple of things. You're actually not responsible for this, but there's also, you can actually find the roots R1 and R2. In other words, this is the problem we solved yesterday. We solved this problem yesterday. It's different than the one we solved today, right? The one we solved today, the one we solved today just had a minus sign. There was also a 3 in front of here, right? But this is the one we solved yesterday, right? Yeah, we solved this one yesterday. And okay. Yeah, we solved this one yesterday and we got this as the roots. It turns out that you can use this equation where P0, remember P0 is just, if we're talking about x is equal to 0, P0 is just x times a piece of x, right? In other words, if we take this differential equation here, right? We take this differential equation here. And divide by 3x, right? We get this. So this is my big, my p of x, right? My function p, which is a function of x, is just 3 over x, and q is also 3 over x. So if I multiply it by x, right? If I multiply it by x, I just get 1/3. Okay, if I multiply this by x squared, I get 0, all right? And it turns out that if you plug those values into this equation here, you can study this on your own. You don't need to, but you can check your answer. If you plug now the values into here, right? This is the equation. Here's the equation right here, right? This equation. And so P0 is 1 over 3, right? And Q0 is equal to 0, right? So now I get this equation, right? And if I solve this for R, I do indeed get that that R could be equal to 0 and R could be equal to 2 over 3. So look at this if you want. You're not going to be tested on this, but you can actually check your results and see if if you got the right values of R1 and R2. So I just want you to be aware of this. You get R1 and R2 without having to to go through the method that we did before. Okay. And let's see. All All right, so here's an example here, where if I had this differential equation here, right? Then in this case here, well, my P0 is gonna be 0, it's just 1, we divide this by here. So in this case here, we're gonna get R, if you went through this, you'll see you get R1 is equal to 3/2. So this is just another example of finding the roots of the initial equation without going through the method of Frobenius. Okay, but you still, if you want to get the coefficients, you still have to go through the method. All right. So this is just another example of the method of Frobenius that you can look at. Okay, we'll see what I did here. In this problem here, let's see. That's not what I want. Okay, I got the roots here using okay. Yeah, I got the roots using this equation, right? I got the roots using the equation, right? And then I got the roots using the method of Frobenius. So this is all using the method of Frobenius, and you get the same roots. So I get the same result. So you could take a look at this, and you know, you could look at this example. All right, so here's another example using the method of Frobenius that you can follow. Okay. Okay, I just want to talk about a couple of things here that I want you to be aware of, assuming that, you know, you're going to continue maybe, you know, if you end up, well, depending upon your major, like if you do physics or even if chemistry, let's say in chemistry, you want to solve the Schrodinger equation and come up with the orbitals, you're going to need to understand stuff like this. But anyway, I want you to understand that there are different cases, okay? R1 and R2, if it's not a positive integer, right, then we're guaranteed that we're going to get two linear independent solutions. Well, first of all, two linear independent solutions are always going to exist. The question is the method of Frobenius going to give it to us, okay? So if R1 minus R2 is not a positive integer, then the method of Frobenius will give us two linear independent solutions. It will give us a solution that looks like this and another solution that looks like this with different values of R. All right. Now, it turns out if R1 minus R2 is a positive integer, well, once again, there does exist two linear independent solutions where C is a constant that could be 0. Okay. So there exists a solution C1, but it could turn out that the method of Frobenius fails to give us a second solution. So I just want you to be aware, but the problems I give you, you will have two solutions, okay? But I want you to be aware that if R1 and R2 is a positive integer, right, that the method of Frobenius could fail to give us a second solution. But there is a second solution, okay? It's just that the method of Frobenius fails to give us a second solution. And it could turn out, and you do have a problem like this on the Weber side, it could turn out that sometimes the smaller value of R, the smaller value R2, all right, may give us two solutions. So it could turn out that that one R value, now this is only when R1 is equal to R2, that one R value gives you the smaller value can actually give you two solutions. The smaller value of R2, I should say the smaller value of R, but the smaller value may give us two solutions, okay? And the larger value will only give you one solution, all right? And then there's a third case where R1 can equal to R2, and there exists two linear independent solutions, but nevertheless, you only get one. Okay, and you could find a second solution where, just think about how messy this would be, where you have to square the power series, and then you have to take the p-value and integrate that. And then it's the integral of this. This is very, very messy. And normally you would do this by computer. But I just want you to be aware of the fact, assuming that maybe someday you'll be solving equations like this where these conditions will occur, that once again, when R1 is equal to R2, it does exist two independent solutions, but the method of Fabinus fails to give us a second solution. But you can always find a second solution using this formula here. Imagine squaring the power series and then doing this integral and dividing the square of the power series times this, then multiplying it by the power series. It's a mess, but nevertheless, it can be done. Okay. Your book may actually have I think your book says it can best done by computers, but talks about this. Okay. Any questions? Because I think I'm done with power series. Okay. Let me just see something for a second. Let's see. Okay. All right. So I'll help you out with the homework. This is the one I want. Okay, are you seeing my screen now? This is question number 3. Find the power series solution about an ordinary point.
Yeah.
You can take a screen capture of this. So this is one of your WebAssign problems. But now this is, with this one here, we don't have to use the method of Fabinus, right? So you can see the solution here. So here now we don't have the n plus r, right? Because I'm not dividing by an x here, right? Or an x squared or anything. So, so you can take a screen capture of this. You will have, instead of this 3, you're probably gonna have a different number. You may look out and have a 3 here. So I think this is the complete solution on one page. I'll continue on the next page. Oh, okay, so this is, all right, so this is question 3. So you take a screen capture of this if you want. I'll give you a second to take a screen capture for those that are not recording. And then here, you take a screen capture of this. I think the problem that I gave you, well, I went out to 1, 2, 3, 4 terms, but you only need to go out to 3 terms on the exam. All right. I think in the solutions, I go out to 4, but you only need to go out to 3. Okay. Does anyone have any questions? So I'm going to start Laplace transforms on Monday, and we'll have the exam on Tuesday, and there'll be some simple Laplace transforms on the exam. Okay. If I just give you power series and you mess up, a problem, you can end up getting a really poor. I think it's your benefit if I put some simple Laplace transforms on the exam, so it's not just power series. Okay, I don't know if I should start Laplace trans. We still got, well, we got 10 minutes. You want me to start Laplace transforms or wait till Monday? We're actually in good shape as far as getting everything done that we need to get done. Okay, maybe I'll, the thing is we save time by, you know, if we were in the classroom, I wouldn't be able to teach while you were taking the exam. So with the remote teaching, we do get more, we do get more time together. So let's see. All right, I'll end it here for today. If anybody has any questions, I'll stay on. So have a good weekend. You know, I made a lot of the assignments due on August 14th, but don't wait. You know, as you can see, some of these problems take a while to do. And also the spring math problems, I pushed them out to August 14th, but don't wait to get them done. So work on them. Okay, well, have a good weekend, and I'll stay on if anybody has any additional questions, and I'll see you all on Monday.
I have a question.
Sure.
Thank you, Professor. You have a great day.
Okay, you too. Yes.
How many problems are we gonna have on the exam?
I'm not really sure yet.
Okay,
Maybe
thank you.
5. So there'll only be 2 problems on power series.